we're going to move on from our favorite red-black tree example, fortunately, and do something entirely different. So today we're going to talk about something called inductive universes, and we're going to see how to apply that to define domain-specific languages. So the first thing I want to do is say what an inductive universe is. And the idea here is that we have a data type that can be interpreted as types. Okay? So you have a hunk of data in Agda. It can be whatever kind of data you want. But there's some way to view this data itself as types. And what this lets you do is it lets you carve out a little space of all of the types in Agda and do some programming with these types. So the simplest possible example of an inductive universe that I could think of is the following. The data type that can be interpreted as types is the Booleans, which has constructors true and false. And then we can interpret the Booleans as types by writing a function that I'll call check, which maps every Boolean to an Agda set. And the idea with check is that check true equals something, and check false equals something else. Okay? And the things we're going to pick for check true and check false are the type unit and the type void. So unit is the one element type. So unit has exactly one element. It's written angle bracket, angle bracket. So it's an empty tuple. And void has exactly 0 elements. Void is the empty type, the type with no inhabitants. So its inhabitants are written like that. And the point is that check turns a Boolean into a type in such a way that there's a term p. Can you guys see here? No. There's a term here. Yeah, OK. There's a term p of type check b if and only if b evaluates to true. OK? So for example, if we check that 2 is less than 3, well, 2 is less than 3, just where less than is just like the function that does less than on numbers, will evaluate to true. So check 2 is less than 3 will evaluate to check true, which will evaluate to unit, which means that the empty tuple has type check 2 is less than 3. Okay? On the other hand, check of 3 is less than 2 will evaluate to check of false, which will evaluate to void, which means we can't come up with a term of type check 3 is less than 2. Okay? Does that make sense? We're doing something a little bit new and funny here, which is we're computing a type by case analyzing a value. So this is something you can do in Agda because Agda has full dependent types where you can write functions that take values and compute types. And the interesting thing here is that we're doing it by case analyzing the value of type bool and picking a different type. Over here it's unit, over here it's void. Okay? What this lets us do is to take any Boolean expression and view it as a type. Okay? So sometimes us constructivists will say that propositions are more general than Booleans. So here's the proof of that. We've now turned every Boolean into a proposition called check, but there are lots of other propositions out there besides propositions of the form check b. And you can kind of see why check B is a lossy thing to consider here, because when we have check B, the only proofs are either the empty tuple or nothing. But we've already seen examples like has BH and things like that, where there's propositions with more interesting proofs than just the empty tuple or nothing. Okay? So basic idea of an inductive universe is you have a data type that can be interpreted as types. And you have this function like check that interprets the elements of that data type as particular types. And the thing we're going to do today is to use this idea of inductive universes to define something called domain-specific languages. And the idea with a domain-specific language is that you have a special purpose language for some particular application domain. And the nice things that basically domain-specific languages are supposed to make it easy to program certain tasks. So you might have special syntax for programming those tasks, or you might have special invariants that hold for all programs in your domain-specific language, or you might have a special type system for your domain-specific language. These are the kinds of things we want to capture. So today we'll look at an example called data description languages. Oh, sorry. Let me know if I need to write bigger for the back too. Yeah, OK. OK. So we'll look at something called data description languages. OK. A good example of this is a language called PADS by Yitzhak Mandelbaum and Dave Walker and Kathleen Fisher from 2006 or so. Okay? And the idea with these data description languages is you want to describe the format of ad hoc data, like file formats on disk or web server logs or things like that. There's just like a bunch of stuff. So you want this language for programming these file formats. And the programs in this language are going to be descriptions of data. So for example, you might have a program that says R is a natural number, C is a natural number, and then you have a vector of vectors of bits of length C of length R. Okay? So this program is describing a file format where you have two header fields that give you the number of rows and number of columns, and then you have a vector of bits of that length. So for example, you might have some string representing 2, and then some string representing 2, and then some string representing 1001. Okay, so we're just describing these file formats. This file format says you have this instance of the file format says you have 2 rows and 2 columns, and then here's the associated data payload. Okay, so does that example make sense? Questions on that? Okay, so the reason this is a domain-specific language is that we're going to have operations that are defined for these programs. So basically, if your programs are these data formats, then the operations that you'll have will be things like read and write. So if, let's see, so let's call this program F. So F is this thing. So if this is F, then I'll be able to say things like write F, and then, I don't know, if I do the one that's over there, it would be 2, 2, and then 1. Let me just write the vector as like a list. So the list 1, 0, the list 0, 1. OK, so there's a vector. So the point is, in my program, I have a vector 1, 0, 0, 1. I can write that vector out to a file by saying, with this file format f, write this value. And then I'll also have an operation called read. We'll, of course, get to the types of these in a second, where read f of the string 221001 would then return that datum. OK? Does that make sense? Good? OK, so the idea is you want to do this kind of thing. And so what do we need to do to build up this domain-specific language in Agda? Well, I'm going to break it down into 4 steps. So step number 1 is define the programs. So we'll do that by defining a data type called format, where the formats represent data formats. OK, so that example I had on the board of 2 header fields followed by a vector of that length and width will be an example of a format. OK? Number 2, so how do we know that when we call read on this string with this format, we get back a value of this shape? Or how do we know that we're allowed to pass a value of this shape to write with that format? So we need some way of linking the data format, which is this program in our domain-specific language, with the Agda type of values associated with that format. OK? So this is going to be another example of an inductively defined universe like we saw before. So here what we're going to have is we're going to define a function that I'll call data, which goes from format to set. And the idea with this is it tells you what is the Agda type associated with this data format. So the Agda type of the example we had on the board before will be, say, a pair of a number and then some other stuff. OK? So this is just like an outline. We'll, of course, get going with this in a second. Now we need to implement the operations. So maybe we can just have Ian do this. So what type do we want? We want to define read and write. OK? So what type should, let's do write first. What type should write have? Write is going to say, write is the way that you run a data format as a way of writing a string. Did everyone get the code, by the way? Like, I didn't say it. The code's on the web page as usual. Yeah, OK. OK, so write is going to say, given any format called f, we're going to turn something into a string. Right? So we want to say, given any format f, we can turn something into a string. But what's the type of the something? It's the data associated with the format f. So write will have type, given any format f, given the payload data for f, we can turn it into a string. OK? So notice how we're using this function data to associate an Agda type with this format. OK, and now what about read? What type do you want to give to read? So we want it to work for any format f. That's clear. And then if you read, yeah.
So you take format, then you take a string.
OK, so let's give it a string.
And then it's going to return a maybe data f.
OK.
Might be able to parse.
Yeah, OK, good. So let's say it returns may be of data f. That is, if there's some file sitting on disk somewhere, given a format f, I can try to read something of that data out of it. And if that succeeds, then if that succeeds, we'll get a data f. And if that fails, then we won't. Yeah? So it's not the file existing, so it's not like actually accessing the file. It's the problem. It's that if we want to read, this kind of thing, this kind of f, but the string doesn't have enough stuff in it, then we might fail, right? So it's the parsing that might fail. Okay? And in fact, to get the code to go through, we want to generalize this a little bit. So what we're going to do is we're going to write a read function that takes a string and maybe returns data f along with some suffix of the string. So it's going to try to parse a element of f off the front and then give you back the suffix. And that's just going to let the induction go through because we want to sometimes we'll need to recursively sort of shuffle some work to do off onto the stack and then come back. Okay? So the idea with read is that it parses an f off of the prefix of the given string and returns that f and the suffix. Yeah?
Should it be maybe data f 10 times string then?
No, because it's either going to succeed in parsing and return the f it peeled off and the suffix, or it's going to fail. In which case, the string is the same as it was before. But yeah, like we'll never want it could return the same string when it fails, but we'll never need it to do that. Yeah. Just because if it returns string, like that string when it failed would just be the string that it had input originally, so we already have that string around. Yeah.
So I guess one way to think about it is that we want the maybe to indicate when we're stuck, because you might get back a string which is shorter, but then you don't want to have to check that.
Yeah, I mean, yeah, right. Yeah, I think this just might be a difference in writing this code functionally compared to writing this kind of thing imperatively. Because if you're doing it imperatively, you might have like modified the string or something. But here, you get the rollback for free because it's functional programming. OK, so those are the things we want to define. But since it's Agda, we should also prove something about our code. So what spec can we give to read and write? Let's think of some invariants that we might want to hold about read and write. Read of, write of something. So if we start off, so let's say we start off in the program. We go out to disk, and we come back. That is, say we write something, and then we read it back in. OK. What do you want to know? What was the suggestion? Yeah. OK. So if we write, so say we start with a value in the program, right? We start with some value in the program. We write it to a string. We'd like it to be the case that read will always succeed on that value. Okay? So we want to know that this round trip is the identity. Okay? And that's sort of viewing this as serialization or marshalling. Okay? So the idea here is that you're thinking of starting from the program. The program has some value. You write that to a string because the program wants to save it or something like that for later, send it over the network. And then if the program later reads it back in that same string, it should get back the value that it started with. Okay? So that's that kind of use of this library. So we can state that theorem. Let's call it read-write as given any format f, given any d, which is a data for f, and given any string s. And then let's first say it as if we read from f, on the string write D, write FD, then that equals sum of D comma the empty string. Okay? And up at the top of the file, I did a little bit of a cheat here. For today, we're going to, by string, mean list of characters. And that's just because the code's a little bit nicer to write if we can pattern match as lists rather than having to work with string functions. So that'll be really sum of D and then the empty list. OK? Need a space before the comma there. Yeah. OK. So that spec should type check. Why is there what? Why is there a string? Oh, yeah, skip that, sorry. Good point. OK, great, better. OK, so does that spec make sense? If I write a value out and then read it back in, I get back the same value. Yeah? So remember we talked about the fact that when you have multiple pies next to each other, you can leave off the arrow. Yeah. Any other questions? OK, so this is pretty good. Are there any other specs you can think of? Yeah, Alexei. Determinism? If you, OK, so yeah, so if you read the same string twice, then it's actually built into Agda that it's deterministic, because every function in Agda is a deterministic functional program. So read of fs. What? No, these are not. These are just functions. Yeah.
So we might want the reverse of read write, where
Mm-hmm.
if we successfully read something from a disk and then write it, then it'll be the same string.
Yep. So we can chase this diagram around the other way, which says, say we start, so if we think of it as doing parsing instead of serialization, then it's the same picture except we've got our roles flipped, right? We think of, there is some text out there that we're interested in. We, the program, read in that text in order to manipulate it or something like that. And then we write it back out. We might ask that if we chase around that way, we get the same string. OK? So yeah, that's a perfectly reasonable invariant to ask for. In fact, we're not going to ask for it in this library. And the reason is it's a pretty strong demand. So for example, in lab, you will define an operation that can possibly violate it. And the way to think about it is, it might be the case that there's multiple different ways to represent the same piece of data as a string. So for example, if you had comma or semicolon separated lists of characters or something like that, you might read in a comma separated list, but write out always a semicolon separated list or something like that. Or if it's a program, you might parse the program and then pretty print it, and so the white space will change and something like that. So it's actually pretty strong to demand that it actually comes back on the nose, and so we're going to skip that invariant. But the thing to keep in mind is really that this library is really doing both serialization and parsing. And depending on which of those you have in mind, you might ask for one of these invariants or the other or both. OK? But yeah, that's the contrast I wanted to make. Great. OK, good. So does the setup make sense? Any questions on what we're trying to do? Yeah? So the reason it's called an inductively defined universe is that the universe here refers to format equipped with this data function. And format is an inductively defined data type. OK? OK. So if it's feeling a little bit abstract so far, hopefully it'll get more concrete when we actually write the code. So let's do that. OK? Let's hack. So what formats do we want? Let's start with some basic data types. OK? So first, we'll make a constructor called bit, which is a format. And bit is going to represent a bit. Next, we'll make a format called char, which will just be a format, and that'll represent a character. Next, we'll make a format called nat, which is going to represent a natural number. OK, and we could keep going, et cetera, et cetera, et cetera, but let's leave it there for base types. So now we want to define a format for vectors. So let's call it vec. And vec is going to say, given any format, and we'll need a space before the colon there. Okay, and any natural number n will make a format. Okay, and so thus far what we've got is one way of making new formats out of old formats, which is given any format, we can iterate it and make a vector of a specified length of that format. Okay, and now let's do a format that lets us just sequence two formats. We'll call it then. So given any f1, which is a format, and any f2, which is a format, we can make a format. So the idea with then is it's going to represent a value of type f1 followed by a value of type f2. Okay. So now we can write things like, yeah, Ian, do you want to just do this one now? So let's define an example called f. So just down below, let's define an example. So, okay, first of all, if we load this file, does it still load? Yes, good. Okay, so now let's make an example. So if we want to define a format representing a number followed by a 2 by 2 vector, what would that look like? So, okay. So let's just call it f, and let's not put it in a module, because then when we go to run it, we'll have to type the module name. So lowercase f, yeah. So f is a format. And now let's define in our domain-specific language a format representing a number followed by a 2 by 2 vector. Okay? Bits. Okay? Okay. So what should that format be? Yeah. So scroll back up a little bit. Yeah. So we didn't actually talk about this. We've used it a few times on the slide. If you write an Agda identifier with underscores in it, in particular underscore then underscore here, what that means is that it gets used in fix. And Agda actually has full mixfix support, so you can define things that have like holes in them. So you can define like if underscore then underscore else, which will be written if then else, like usual. But OK, that just means that then will get used in fix. So nat then, OK. And then what? Yeah, parentheses, vec, bit, two, yeah, so like the type argument comes first. OK, but so there what we did was we described a format that describes numbers followed by 2 by 2 vectors of bits. Yeah?
So do we need the outer?
No, we should be OK without the outer parentheses. Yeah. Yeah. OK, good? All right, so thus far we've just written down that like thing as an expression of this domain-specific language. Now what we need to do is we need to implement the functions that imbue it with meaning. Before we do that, let's go up and add a couple more constructors to format, just because it's going to be a little bit illustrative. So below then, we can add a constructor called done, which is a format. And you want to think of done as kind of end of file. So done is going to be a format with no data that succeeds. OK. And we'll add another one called error. And error is going to be a format with no data that fails. So read of error will always fail. OK? Yeah? OK. OK. Or, so like last time we like, if you flip it, is it better? No. OK. OK. Can we just, yeah. Does anyone know how to turn down the lights in the room? Ian, can you just make it bigger, first of all? OK, great. Thanks. OK, not quite that far. Okay. Okay. Yeah. Okay. Let's see. Can we change the color of the purple to something else? No? Yeah, just how much bigger can you make the font? Yeah. Okay, good. Yeah. Yeah. Okay. Better? No?
Like, we're gonna start running out of screen real estate.
Yeah, we can make it smaller then. Do you want to just come down to, yeah. Yeah. Okay, sorry about that. We'll change the colors for next time. Okay. I guess last time we didn't talk about that many data type constructors. Fortunately, there shouldn't be that much else purple for now. Is that better? Okay. Yeah. Okay. Okay, so now what we want to do is we want to define data of f, right? So we've got our formats. We want to now interpret them as Agda types. Okay? So let's say, how are we going to do this? Well, we want to case split x. Okay? And then we get cases for all of the various formats. And let's rename, just go through and rename the subsidiary x's to capital F's, just so it's a little bit easier to read. Okay. So what is the data associated with bit? It's going to be an Agda value of type bool. If you want to follow along, also, the lecture 3 finish.agda has exactly this code in it. So if anyone's having trouble reading, you can read along there, because we're transferring it up there. OK. So the data associated with bit is going to be a Boolean. Okay. The data associated with char is going to be an Agda character. So these are just the corresponding Agda types. The data associated with nat is going to be a natural number. The data associated with, let's actually do then first. So what's the data associated with a format of the form f1 then f2? Pair of data f1 times data f2. So notice that here we're making recursive calls. So the format is defined inductively, and we do recursion on the format to compute the type of data. Okay? What's the data for a vector? So did people do this exercise in lab last time, where you defined a list indexed by its length? So that type is traditionally called, oh, Ian, if you open up preliminaries.agda, yeah. OK. And then search for vec. Yeah. So the answer to that lab problem is this data type vec, where nil is a vector of length 0, and cons says, given a vector of length n, you make a vector of length successor of n. OK? So this is a list that tells you its length. And that's traditionally called vec. And we'll use capital vec to interpret lowercase vec. OK? So if we could, yeah, Todd. Yes. So Agda has constructor overloading. So that nil and cons is different than the list nil and cons. But it's just resolved by types. It's not anything fancy like type classes or anything like that. OK? Good. Other questions? OK, so we interpret little vec as capital vec. So it's going to be a capital vec data f n. And then we'll interpret done as unit, because done is the end of file thing that always succeeds but has no data. And we'll interpret error as void, the empty type, because it always fails but has no data. OK? So now what we've done is we've defined a function that for each format gives us an Agda type. So if we go down to our example, let's make a value called example, where example will have type data of little f. Okay? So little f is the format that specifies a number followed by a 2x2 vector. Okay? And the thing to note is that if we look at the type of the goal here, Agda has normalized the type of the goal to say it's a dependent pair type, because times is a degenerate dependent pair type, where the second component is a 2x2 vector. So the way to prove that the right thing is happening here is let's write down a value like, I don't know, 4, comma, question mark. Okay, so it accepted 4 as the first component of data f, because 4 is of type nat, and the first component of f is little nat, and the data associated with little nat is big nat. Okay, and now we can write down a 2x2 vector, maybe like 1 cons 0 cons empty as the first component, and then put that in parens, and then cons that onto 0 cons 1 cons empty as the second component. Okay, and then cons that onto empty. Okay, so it'd be nice if we had like list notation, but oh yeah, sorry, we said bits, not, so we can't write numbers there. So let's just do false or true, false. Yeah, sorry. So true, false, false, true. Okay. And then we should be able to refine. Okay. So the point is that this function that interprets our data formats as types allows us to supply regular old Agda values like that as elements of data formats. Okay?